This lecture is being brought to you in part by the generous gifts of these sponsors.
Thank you so much, Alan, and thanks to IHMC and to UWF for the chance to give this, and the smart endowment for funding the opportunity. So tonight, what I want to do is tell you about some work that actually has taken place in the Beckman Institute at the University of Illinois. And our group is trying to invent materials that we call autonomous materials. That is, they somehow are able to sense their environment, and in particular, sense damage, that damage has occurred, and then how to respond to that damage. Ideally, like ourselves, we respond to damage by repairing that damage. And so about 25 years ago, my colleague, who unfortunately passed away in May, Scott White, who battled cancer for 5 years, but Scott pulled together a team that allowed us to really, I think, bring together from different disciplines, from aerospace engineering, materials science, and then myself from chemistry, a team that really has continued to work throughout this period of time. And of course, I'll try to mention the students who have done the work as we go along, but a lot of the credit really belongs to my colleague, my former colleague, Scott White. And so what I want to say tonight is really a work that any of the four of us could have given, and the talk really is intertwined between the invention of materials, their function, and then thinking about the chemistry that needs to be developed to go into that. But to motivate the area, I'll start with this slide, which is one summary slide from the report card that was put out by the American Society of Civil Engineers in 2016. It basically says it's going to cost us a lot of money to think about all of the problems that we have with our infrastructure. Of course, those problems, roads, bridges, railways, infrastructure that is largely based on structural materials that encounters through their environment damage over time. It's going to cost us, where's that $2 trillion going to come from? That's a good question, but if we don't, there's several more trillion on the table that will be lost through loss of jobs, through loss of trade, and so on and so forth. And I just lifted one sentence or so from that report because I think that much of what our group, our team had been aiming for was to think about materials that could replace the contemporary materials that are in infrastructure and deal with this idea of enhanced resiliency, because self-healing is really what resiliency should bring. And then we wanted to take advantage of thinking about the whole life cycle of the material, from manufacturing to end of life. And plastics these days, our end of life is all about the news and the straws that are in our oceans and things like that. And so clearly, as chemists, we've learned to put materials together, but have done a much poorer job learning how to take them and return them back to where their original materials. A lot of what I'm going to tell you tonight is really pretty forward-looking. We're not too much ready to put into commercialization yet. However, I thought I would start with one commercial reality. It's actually the only commercial reality that I know of at the moment that really has this self-healing capability in it. It's been a long time coming. It came out of original work that we did in around 2000, but you can't read it. This is RUST-OLEUM. It's a coatings manufacturer. It's actually based in Illinois. I don't know. Has anybody ever heard of RUST-OLEUM before? So, all right. So it's not that foreign. RUST-OLEUM carries a product called MetaPrime, which is, as you can maybe read if you're sitting in the first row, patented self-healing technology to extend coating lifetime on surfaces subject to damage. And so scratches and so on and so forth are repaired. This is a primer, and it's particularly useful for things like infrastructure, steel, corrosive underlying substrates. I presented only from the lessons learned. This was technology that was invented around 2001. It's taken that long to get it to the marketplace. Why? Because, I mean, if it's going to last longer, it needs to go through really long aging tests before anybody is even willing to use it. And this product is selling really poorly right now. Here's the deal. We promise twice the lifetime. Actually, it's probably rated for 3 times the lifetime of its competitive technology. It costs 40% more, and so the value added, is something like 140%. But the question everyone asks is, who else is using this? And right now, of course, nobody is. So it's kind of hard to break into the market, even if you promise, something that isn't currently offered. So I just wanted to put this up there only from the standpoint of this is exactly how most of what I'll tell you tonight got started. It was many skeptics and far, distant from any commercialization. Took 2 decades to bring it to the marketplace. And a lot, I think, of what I'm going to tell you tonight is probably, that kind of forward-looking. I mean, when we start thinking about replacing the materials that go into the fuselage of commercial aviation, you're not going to want to put just something that hasn't been put through the test and then jump in the plane and fly it. So that's, part of the resistance to bringing in new materials. This is a plot. You'll see it a couple of times. And then I need to tell you one thing about that's really important about tonight's talk, and that is the first story that I'm going to tell you is about 10 times longer than every other story that's going to follow. So don't get too frightened when you learn that, much of what I'm going to tell you tonight is about new ideas in manufacturing. So here's the life cycle of a material. You'd like it after manufacturing to be at 100% of performance. If it's a structural material, you hope it carries the load that it's supposed to, but it's going to encounter in its environment and through mechanical forces, damage, that's going to lower that performance. And somehow you'd like that autonomous material to know that it's been damaged, to kick in some repair mechanism, recover that performance, and do this repeatedly as much as it needs to. Ultimately, there will be a point where there will be an end of life, an irrecoverable state will be reached. But along the way, you'd like this to self-protect. That is before any damage has occurred, but maybe there's a particular region that's carrying more of a load than other regions, and so you'd like them to be self-protecting regions. You'd like there to be some kind of report out that is, warning, you may want to check this part, it's been damaged, so self-sensing capabilities. Then, as I mentioned, return back to normal levels, self-repair or self-healing. And then at the end of life, what you would like to do, and I'll give you one demonstration of this later on, is think of your cell phone when instead of, it certainly, most of the materials in your cell phone last longer than the software and the basics hardware that's into it. And so you have to return it and it goes to the electronic graveyard. But it would be nice if you could just dial in a code and have the phone sort of self-destruct and return to useful components at the end of its lifetime. And so, could you trigger transients? And then the last thing is, there are some amazing biological species that can kind of regenerate. Bone actually is a biological material that can regenerate it. In other words, it can grow. And chemists don't know anything about making materials grow without sort of manufacturing them in traditional ways. And so regeneration is another one of the stories that I'll mention. So just for the sake of tonight's talk, we're going to spend a lot of time on some new work on manufacturing. And then I'm going to touch on each one of these, but literally it's going to be like a one-slide story. But each of these could have been expanded into a full story if time permitted. I'm going to teach you something about chemistry that's known as FROMP, which is fun to say, but it really is an acronym that stands for Frontal, the front that's going to come through tonight when the weather comes. So that's exactly what front is referring to. And then ROMP, the ROMP behind that is ring opening. So this is a chemical structure. It's got rings. Ring opening means we're going to open one of those rings. And then the M is metathesis, which is a word that just means exchange. And so we're going to exchange pieces. This vertex here is a carbon. And I must have had too much coffee this morning. I can't keep the laser pointer still. And then another carbon over on the other side. So metathesis is an exchange reaction. It's replacing this with that. And then P for polymerization. So we're going to go in and you're going to learn about FROMP. That's what you can take home. The take-home message is, what did you learn tonight? You can say FROMP. I learned about FROMP. And so, like I said, it's fun to stay. So at the bottom, these are our toolbox of concepts that really go into the materials ideas that are at the top. So fiber reinforced composites, I actually just saw some really fascinating composites that are, the shell casings of the robotics. We see them in things like, so wherever lightweight, high strength is needed. And so, things like the fuselage of the Dreamliner, the Boeing 787, incidentally, not the 737. The Boeing 787 is the Dreamliner. Wind turbines, which are, I'm sure, cropping up all over the place, lightweight, high-strength structures that can handle these fatigue loadings, meaning like the wind is blowing on and off, on and off, on and off. And so that deformation has to, that occurs has to be able to be tolerated somehow without causing damage. And so the structure of composites looks something like this. It's a woven mesh of carbon, often carbon fiber. And then in between the white spaces here, which is a cross-section of that woven mesh, the white spaces are a polymeric material. In fact, mostly epoxies like you'd get at the hardware store. And so it's about 50% carbon and 50% of this epoxy material. And a lot of it is interface. If you think about just all of the surface area in that epoxy material, and that goes what's making the wind turbine blades or what's making the fuselage of the Boeing 787. And this is a plot over here that's comparing a specific strength, in other words, how strong the material is normalized by its mass. And so, for example, the high strength and light weight of composites really make it go very high on this specific strength scale. So carbon epoxy is really the ultimate material compared to glass epoxy or wood. And if you compare them to just the components themselves, things like aluminum are way down here. Epoxy by itself without the composite is way down here. So these non-composite materials don't compare with these composite materials. And the wood, which is nature's composite, is really right up there with the rest of them. The problem with composites is they've got a lot of life cycle challenges. They're costly to produce, and they leave a big footprint behind in their manufacturing. The CO2 footprint, for example, is very large. And they're damaged not so easily, but when they are damaged, it's difficult to detect and almost impossible to repair. Here's the, in case you're wondering how long composites have been in aviation, you can see that starting in the 90s, there was really an influx. And so the 777 was the first commercial airline that had a significant amount of composites, 12 weight percent, and it was about 50 weight percent aluminum. And that started switching over with the 787, the Dreamliner, which you can see from this schematic. The navy blue or that royal blue is basically where the composite materials are. So huge amount of composites are going into into aviation these days, starting around about a decade ago or so now. Let's take a look at the life cycle assessment that someone has done. We didn't do this, but starting from the manufacturer all the way through to use through disposal, what are the advantages of materials like a composite compared to aluminum? And so this analysis was done on just two sections, and this is a really interesting story about how the Dreamliner is put together. Dreamliner is this massive airplane, and And it's put together in these sections. And if you're sitting in the front, you can see that these different sections are manufactured in Japan, in Wichita, Kansas, in Sweden, in Canada, in the UK. And you might say, why in the world is this airline manufactured globally and reassembled all and brought back together and put back together in I believe it's in North or South Carolina? And the reason is because to get global buy-in that, yes, we'll allow this aircraft to land on our soil if you allow us to manufacture or get involved in the manufacture of some component. And so there was really this political component that went into deciding to do this manufacture, this global manufacture. Well, the analysis was done on these two tail sections labeled 47 and 48, and those are those sections right there. And it basically is the composite is cured 8 hours at about 180 degrees Celsius, so very high temperature for a very long time. Hence, a lot of energy goes into this massive part and its curing. And this is a plot that was out of that paper. Carbon dioxide emissions, that's the black bars. We'll just pay attention to that. Very low footprint, very little energy for aluminum manufacture and disposal. This is another scenario where the aluminum is actually not recycled. In this case, the aluminum is recycled, so you can see it has a lower footprint. But you can see a much higher carbon footprint for the carbon fiber composite material. And it's largely due to this 8 hours of curing at 180 degrees Celsius in a huge autoclave, which you can see on the next slide. So there's an individual person. This is the fuselage section, a section of the fuselage, one of those components. And by the way, I didn't tell you the rest of the story of this manufacturing process. So now that you see the scale of what we're looking at in terms of this fuselage, one section of it, in order to move all the parts to the place where they're going to be assembled, there was another aircraft that was built. Rather than just putting those parts on a ship and shipping them across the ocean, they were flown in by the Dream Lifter, which carries the components of the Dreamliner to where they need to be. Imagine the size of that tube, that houses these different fuselage components. And there's a mold for a wind turbine. So these are massive manufacturing operation. Now you see the large outlay and capital expense. We were challenged by our program officer who said, there's really been no new disruptive change in how composites are manufactured in the last 30 or 40 years. And we wanted to think about getting around this energy-intensive process. And that's where we started thinking about different chemistry, polymer chemistry, that might come into play. And here's FROMP. So right away, you'll get a chance to see what FROMP is. Notice there was a soldering iron touch at the very beginning. This is liquid. It's the raw material. It's colored orange because of a catalyst that I'll show you in a second. This is now hot, very hot. This is cool, room temperature. This is the front that's moving through in a very nice, controlled, steady rate. And this is sped up 3 times, so it's a little bit fast. But actually, we have samples right now that will go actually faster in real time than what that movie did. And so that's what FROMP. What is FROMP? It's a propagating reaction wave with a front. It's what I would like to call a carefully controlled chemical burn. I mean, burning is basically a fuel being consumed. Our fuel is the raw material that actually transforms into a useful structural material that has comparable properties to any epoxy. The whole process is driven by the heat that's given off in that chemical reaction, the polymerization reaction, and the process is scalable. Here's an example of like a 2-liter Coke bottle. There's a nichrome wire that just gives a little bit of heat to ignite the controlled burn of that frontal ring opening metathesis polymerization. 2.5 liters about of DCPD, which is our monomer, dicyclopentadiene. It comes from a petroleum byproduct. Nobody knows what to do with it, except it clearly is potentially at least useful as a material. It's now used as jet fuel, basically because nobody knows what else to do other than put it in in a jet fuel and use it for that purpose. GC2 is really important. It's the Grubbs Catalyst 2. Grubbs was my postdoctoral advisor, and I learned about metathesis polymerization from him and his group. And then there's this magic thing that we added, which I'll tell you about, because if you mix the catalyst with this raw material, the monomer, you would expect that it would take off right away. We wanted to be able to stabilize it as this water viscous liquid that we could move around and manufacture, but then spark it with a little bit of heat to basically cause this reaction to take place. So I figured this next slide is our stretch slide. And what I mean by that is you all came here tonight because you wanted to hear some, science and learn something. And so I'm going to stretch you on this slide. If you don't get everything, that's okay. There's going to be some if you don't like mathematical equations, that's okay, because I've tried to weave the math in with the picture. And the whole idea is to try to get an understanding of how does this frontal polymerization work anyway. So this chemical structure here is our monomer. It basically fills most of the box. We have a tiny, tiny amount of catalyst, which is a ruthenium-based catalyst. That's that thing up at the top. And this is a really small volume element. Think about it as like something much smaller than a millimeter. It's actually shrink it way down. And so what we're going to do initially is the wave is going to propagate from left to right. And the way it works is it needs something to kick it off initially. And so the soldering iron touch or the nichrome wire gets us started. And then chemistry takes place. In this particular, our magic ligand, the TBP that was in the last slide, basically comes off, and that's a heat-induced dissociation, separation reaction that makes now the reactive state green of that catalyst. And so now it's ready to roll. And what does it do? It undergoes FROMP in that box, which is transforming. So the ring opening part, this red-colored ring opens up and then joins with its neighbor and basically makes a long string of a polymeric material. That's giving off a lot of heat in doing that, because this ring doesn't really, it's like spring-loaded. The ring doesn't want to be a ring, it wants to open up, and the catalyst basically provides a pathway by which it can open up. And when it opens up, there's a lot of energy that is released from that spring-loaded ring that doesn't want to be a ring, it wants to be opened up. And that's where all the heat comes from. And so at that point, we're generating a lot of heat in that local region where that reaction started. And here's the scary part, which is going to stretch you. It turns out that the reason this is a controlled burn is because there's a nice interplay between how the heat is transferred and how the chemical reaction unwinds. And the two, this is not unlike trying to predict the weather. I mean, the weather is pretty much a set of coupled mathematical equations like this is, and so we have a pretty good understanding. This top reaction is known as the heat transfer equation, and the bottom reaction is known as the Arrhenius equation. And the key parameters that I'll show you are how much heat is released. That's what's given by that capital H. And then we have some like, how fast is that heat released? Alpha is how much fuel in that box has been burned. And so initially none of it, and then by the time we're done, all of it. And so 0 is none, and 1, alpha will go to 1 when it's all consumed. And so how fast this is just like a velocity. That's really the way to think about it. And so what happens next? Well, that is coupled into this Arrhenius equation, a very strong temperature dependence. That reaction rate is very strongly temperature dependent, and that's really all you need to take away from this slide. It's multiplied by how much fuel is available, and eventually when all of the fuel is consumed, alpha goes to 1, which basically means this last term goes to 0. And then what happens is, well, you generated some heat and you released it pretty quickly, so the box is going to warm up. That means we're going to have a change in temperature in that time period, and that's going to not stop there, because there's a place for that heat to flow. And so this kappa term in front is like a diffusion or a transfer of heat from one box to the next. And so when that happens, everything starts all over again. And before long, now you've been stretched and learned about this controlled burning process, which is an interplay between a heat diffusion, heat transfer, and a chemical reaction that's very temperature sensitive. So why did we choose the dicyclopentadiene for our frontal ring opening metathesis polymerization? We need something that is reactive. We want it to produce a very useful material, and it needs to be chemically controllable. And here's the main chemical players. Don't be too frightened. There's the ruthenium that I was talking about, and it's surrounded by all kinds of other chemical entities which make it work in the way we want it to. And then there's dicyclopentadiene. Our catalyst is able to cause a lot of heat to be released from that dicyclopentadiene ring that opens up. The dicyclopentadiene is a really high temperature, really excellent material. It's tough as can be. I'll show you some movies in a little bit, and then the question is like, well, everybody that knows precious metals, if you pay attention to the precious metals commodities, you'll know that ruthenium is like up there with all of them. And so then you wonder, like, could you ever really make a fuselage cheaply enough out of ruthenium? And the fortunate thing is catalysts, when they operate well, you don't need very much. 10 ppm is a really tiny amount, less than 1% of that liquid is catalyst. And so a typical 787 fuselage would have about $1,300 of ruthenium flying around for its lifetime, 30 years. And then at the end of the lifetime, you can decide whether it's worth trying to recover some of that ruthenium or just let it go back into disposal land. The problem is the initiation is too fast. And in general, when you mix that catalyst with that monomer, we need to somehow control it better. And that's where my student, Ian Robertson, came up with this chemical, which really blocked the polymerization at room temperature from taking place. It didn't block it completely. The liquid, that is like water liquid, will polymerize slowly over time. And it's kind of interesting because when it polymerizes slowly over time, it creates a gel-like structure. We're all familiar with gels, gelatin, and that's what happens to this. And so Ian discovered, he could take that gel, which is largely still that liquid monomer, but now it's been gelled to a point where he can mold it and bend it and shape it. And there's still enough liquid monomer in that gel, just like gelatin has a lot of water, that he can take a soldering iron and then trigger that gel to begin to undergo the rest of the polymerization. The rest of the monomer can polymerize. He had to get his finger out of there because it's getting kind of hot as that frontal ring opening metathesis polymerization takes place. But now Ian could literally jump on top of this and it wouldn't deform at all. So he took what was a liquid, transformed it into a gel, and then now into a really structurally sound material. And chemists like plots like this, but it's basically saying, all I'll just say is we can control this reaction with great fidelity. And that allows us to do things like composite manufacturing. And so for those composites that make the fuselage or make the wind turbine are basically fabric that are woven, and that fabric is made out of carbon fibers, really stiff and strong, and then we would wick our liquid monomer into the fabric, and then we would ignite the frontal ring opening metathesis polymerization, at least in theory. So if we had a wire that was going to heat up, we'd get a traveling wave that would look something like that. And so this is kind of the side view of that. So we basically infiltrate or infuse in a lot of this liquid, and then we ignite it. And on the next slide, you'll see what's an infrared camera looking at an object. So it's going to be, the infrared camera is color-coded so that blue is cool and red is hot. And so on the left-hand side on the next slide, I got to tell you this because as soon as I hit next slide, it's going to begin to play. On the left-hand side is a movie that's going to be in this configuration. And on the right-hand side is going to be a configuration where we've heated the bottom and we've set the composite on top, and it begins to undergo the reaction. And so here we go. You can kind of see we heated it up, and now in the composite being synthesized in real time. And so this one, you could see the wave was going through the thickness of the material, and it all came through very quickly in one fell swoop. And this is a nice, carefully controlled polymerization through the composite material, well behaved. They're both very well behaved, and we can now instantly make these composites with really little amounts of energy. Basically, whatever it took, for example, to energize the start of that reaction with a little bit of heating of a wire, or in this case, setting it on a hot substrate. And so just this is a kind of an amazing plot. It's basically how much energy is consumed versus how much time it takes to cure it. And so once the front gets going, imagine on this fuselage, if you just started it in a single point, it'll spread. And before long, it'll spread all around the circumference of the fuselage. We haven't done this, by the way. We've not done the fuselage experiment yet. But imagine it's going to spread all around the fuselage. And so over time, you're polymerizing at any given moment a lot of volume at any given instant of time. And so basically what it means is that the time to cure normalized per volume is you're polymerizing a lot of material at once from a relatively small amount of energy. And so again, on a plot that shows orders decades of change, every line is a factor, every major line is a factor of 10. The fuselage is going to be consuming very little energy and being manufactured very quickly. And these are the kinds of parts that we've manufactured with frontal polymerization. You can get this corrugated object, or you can get these nice panels, and they're really performing at the level of conventional composite materials. And this is just strength and stiffness on these plots. And the main thing to take away is, well, they're all about the same, including our liquid frontal ring opening metathesis polymerization composite. When they fail like that. They're really very tough. And we have a long ways to go in terms of making them. I mean, we've not been doing this very long. Composite materials have been manufactured for decades. And so there's a lot of areas that we know we can improve on, like that interfacial region, which is where most of the damage takes place. Last thing, this is kind of fun. This is a 3D printing where this substrate is hot, and then this is our ink, our dicyclopentadiene and catalyst. And what you're going to see in this movie is we're going to print that liquid, and that liquid will touch the bottom, ignite the front, and then the front is going to chase the print head. And so right behind the print head, we can move it in any way we want to, but then right behind that print head, the front, which makes the rigid material, is going to be chasing the print head. And so it becomes solid right after that. And so if you watch very carefully, you'll be able to pick up where the front is. And so it's started, it's right there. You can see the front is chasing the print head, and it always stays at about the right distance. This is now very solid, so you can print 3D structures without worrying about that it's going to collapse on itself. You can make freestanding 3D objects at a reasonable rate. We can go a little bit faster than this is sped up 3 times, and we can even go a little bit faster than this right now. And when it's all done, basically you can, I think it's going to end in just a moment, see what this freestanding structure that came out as a liquid and was almost instantly transformed into this rigid solid body. And we can manufacture all kinds of different shapes. And my favorite as the chemist, of course, is this particular rendition of a dicyclopentadiene monomer that actually made the material that it printed. So that's the manufacturing story. That's the long part. You survived 30 minutes, and the good news is the rest of the talk moves along at a little bit faster pace. So self-protecting, one would like to be able to imagine this region where damage is occurring, to use that force to trigger a chemical reaction and maybe stop that process from taking place. And so we invented these things called mechanophores, which took advantage of force to undergo a chemical change. And I have to say, so far, this picture, which was about now 10, 12 years old, has never been realized yet in its ability to, say, stop the damage, protect the material ahead of time. But we have at least been able to do what's next on this slide and use that same concept of force-induced reaction as a sensor of damage. And so I won't show you much of the chemistry. I will just show you really one movie. And so imagine, here's a molecule. Imagine it to be like that 3D printed molecule that I showed you. So put that structure in your mind. And if you pulled on it, you might expect it to break open in certain places. And it turns out this molecule, if you pull it from these 2 points, which happens to be the point 5 on this ring, and so it will undergo this chemical reaction, and it will change from colorless to colored. And so here's the movie, which is about the only thing I really want to show on this slide, is in real time. It's a little bit hard to see, but you can see that there was a color change to a more yellow color, and if my student Max Rob releases that, it would return back to its colorless form. And you can see what it looks like better in the image that's up there. So that's the self-protecting and self-sensing. And what about this self-healing concept? Well, that primer, metaprime, that I showed you is really based on the idea that when damage occurs, like when that coating is scratched, if we could release liquids that would flow into that damaged region and then in contact with, say, a second component, that's why there's a blue and a red colored sphere, they would cause a chemical reaction to take place and basically fill that crack and repair the damage that had taken place. And that was the original idea. You'll notice the year 2001. So this was really the first example of self-healing material based on these microcapsule containing self-healing agents. And in this case, when damage of a crack encounters that microsphere that contains a little bit of liquid, it releases that liquid. That liquid encounters a catalyst, much like GC2, Grubbs Catalyst 2, and then causes a polymerization to take place. There's voids left behind, but the main thing is the large area damage has been filled and repaired, and that's what this this plot is all about. We're looking at growing a crack by fatigue damage. We're basically causing, through oscillatory loading and unloading of a specimen, it might look like that, and the load would go in the vertical direction, but it would be oscillating, fatigue loading. And so how fast does that crack grow? In the control sample, the knead epoxy, it grows very quickly. This is the number of cycles that we've loaded and unloaded. So you'll notice it's millions. These experiments take a long time. Fortunately, our students still graduated in reasonably like 4 or 5 years. But they do take a long time, oscillating at about 5 hertz to get 1 million cycles. You can do the math yourself. Here's the self-healing material. You can see it started to undergo damage. Crack was growing, but it then it stopped because of the self-healing capabilities. Much better than putting the self-healing components into a capsule is a vascularization. And so here's an example of a composite that has been vascularized, much like, we're vascularized. And instead of delivering those healing components from capsules that break open, we're delivering those from vascularized structures. And again, red and blue, because we need 2 chemistries that can only come together when damage occurred, so delamination, breaking apart the layers, filling the space, those 2 components mix, and then they polymerize, they rebond those interfaces back together, and we can do this. And the advantage of the vascular structure is that you can repeat this over and over again, whereas the capsules would release their contents once and basically be all finished. Finally, triggered transients, what you want your phone to do when it's end of life, it's time to get a new one, requires some new materials that we call multi-state materials. The recycle button is really the key point. And on this slide, I'm just going to show you really this demo up here, which is based on a polymer that undergoes a depolymerization reaction. I said we, as chemists, learn how to put polymers together, materials together, but have done a lot less with thinking about taking them apart. And fortunately, this is beginning to change. This material, without a trigger, which is something like a chemical trigger or a thermal trigger, is quite stable. And this packaged electronic is packaged in the clear material, a film of CPPA, for cyclic polyphthalaldehyde. And when you heat that, it will, in the absence of a trigger, a chemical trigger, what this is, will basically, in the absence, it will stay put. And it's basically robust like you want it to be. Like if you left your phone in the dashboard of your car, it's not going to disintegrate. But if you put the chemical trigger in and then you coated it to like heat up to 111 degrees, this is what happens, right? So the packaging goes away because it undergoes this return back to monomers. And then as soon as the packaging goes away, well, those electronics are made out of silicon, a very thin silicon, and it reacts with air, and over time they'll basically return to sand. And so the monomer vaporizes, and that's the after depolymerization, the monomer vaporizes at that temperature, and the silicon will ultimately return into some simple component. So the phone disappearing idea is not ready for prime time yet, but we're thinking about it. So let me tell you a little bit about vascularizing composites, because I think this is a really exciting area that I had some conversations with this afternoon. And I'll just say that, what we're trying to do is use that depolymerization process to make those vascularized composite structures. What would be really interesting is, this is an idea that came out of the students, and this is what happens when you bring students together from different disciplines, and they start talking, and they're the ones generating the ideas now, not the faculty members. And so what they said is, like, couldn't we do it all at once? Do the FROMP manufacturing together with the depolymerization. The heat from the FROMP could drive the depolymerization reaction of CPPA, and we'd make a channel, a vascularized channel, where that fiber of CPPA was. So this material depolymerizes, returns to a liquid, and so what's going on here is, there's our gel. Remember the gel that you saw Ian do? Here's the front, and the front is going to now drive, the heat from the front is going to transform the monomer or the CPPA fiber back into monomer, and the monomer that's in the gel is going to be converted into polymer, all with the same heat that was just initiated from the very get-go. And this is an expansion down on the bottom of that blue box. And so you can begin to see something happening. The front's going through. As the front goes through, depolymerization takes place, and a vascular structure is created. There's the channel that was created. This is a negative of that channel, so you can see the structure of the channel really is well controlled, and this is a pretty robust process for us to be able to perform in a variety of different configurations. Like, this is a thin film. It shows sort of just a branching effect. So the depolymerization follows the branch, and the front is there, and so it's really turning out to be quite a robust technology to simultaneously vascularize composites while they're being manufactured using the heat of that frontal ring opening metathesis polymerization process. Almost to the end, this last idea is really the growth idea, and I'll just give you, like, how do you fill a hole that's been damaged without gravity causing these liquids to basically drip down before the hole is filled? And what we invented was some chemistry that gelled in that space, first as a like gelatin-like structure that allowed it to fuse together without dripping down. And then finally, once that gel had filled the hole, in time, a second polymerization took place harden that material and restore it to its final form that has the functional properties of the original material. It's hard. I mean, we take growth of biological things for granted. Chemists just don't know how to do chemistry in the wild yet. I mean, we like to do chemistry in a flask as opposed to the challenges that nature has to deal with. So this is kind of our motto of this sort of life cycle control process: live long, be fit, die fast, and leave no mess behind. And if we can accomplish that, I think we have achieved the healthy aging of materials. What I want to do now is just, since it's 43 minutes, and I'll take just maybe 5 minutes more to kind of tell you what we think is the next big frontier. And the next big frontier for us is to think about putting reaction diffusion systems into a different kind of manufacturing. And so, you know, we all have a hand, and if we all looked at our hand, we'd say that's a hand. It has the recognizable shape and form and function of a hand. And yet it started from a spherical ball of cells, and then biological development took place, and digits formed over the process of, you know, development. And how does that take place? Well, it takes place by the same concepts that are embedded in frontal ring opening metathesis polymerization, reaction and diffusion. In FROMP, diffusion was the transfer of heat. And in developmental biology, diffusion is the transfer of mass diffusion. And what that ultimately creates is a set of conditions that started from a spherical ball cell, and somehow this idea that, you know, our hand isn't a spherical ball of cells anymore. It has a symmetry that's different than that. And so symmetry had to be broken from this very highly symmetrical spherical ball of cells into this form and function shape. And wouldn't it be great if we could manufacture on the fly materials like that? And so at the bottom is the only thing I want to draw your attention to, is a frontal polymerization that's taking place. And it starts with, you know, a homogeneous liquid. There's a fiber embedded in it, which is nucleating off that fiber void structures that begin to look like the void structures in leaves. And so, you know, we're just being tantalized in the lab with the idea that, you know, we're not using any deterministic process to create structure that now is a vascularization that looks very much like a leaf. And we would really be able to, I think, make major progress if we could manufacture components that could take advantage of these symmetry breaking processes. And things as complicated as the seeds of a dandelion, they all look the same. How did they get there? You know, it's amazing that, you know, there's basically a reaction diffusion process that is behind all of that. And so we'd like to learn and understand that. And I'll tell you, this slide will take the longest, and the rest of it will go fairly quickly. But here was an experiment that we were trying to model in the lab. Philippe Gabel, who I showed on the first slide, is our computational person. And all we were doing is, this is a glass on the left and on the right, and it's a sandwich, and in the middle is the liquid monomer that's going to undergo frontal ring opening metathesis polymerization. And what happens is, if you reduce that gap smaller and smaller and smaller, eventually all the heat that's being generated from that reaction is transferred into the glass. And so then the front doesn't propagate anymore because it doesn't carry on to that next cell, like I showed you in that stretch slide. And so the frontal velocity, which is plotted on this axis, is 0, because all the heat, so if the width, W, is too small, way over here, it basically just dies out. The experiment is the red box, and the modeled behavior is what I'll show you on the next slide, is the triangle. And so we were getting good behavior, good agreement between experiment and so if, you know, you're down at 1 millimeter thick or so, we can't propagate the front. But if you get up to 6 millimeters, no problem, the front is very stable, and the velocity doesn't hardly depend anymore on the thickness. But what's really interesting, and what was noted in the model, and then noted in the laboratory. And it's important to mention it in that order because normally experimentalists like my group like to say, yes, we experimented and discovered it, and then the modelers came along and said this is the behavior of it. But in this case, it wasn't. The modelers actually saw something in the lab, on their computer, which then my experimentalist said, oh, we might have seen something like that. Let's go back and look at it in the lab. So here's the three. This is 6, very well behaved. This is all computational model now, just like modeling the weather, modeling FROMP. And here's what happens when it sort of peters out. It starts, and then all the heat is being drawn out because there isn't enough monomer in there, and so it just kind of goes away. And then what happens in that sweet spot, right in between, is something that begins to think like, wow, maybe there's interesting ways to use reaction diffusion. So it starts pulsating and behaving like this, no longer this steady state, nice behaved front. And then my students are like, well, I think we can mimic that sweet spot in the lab. And this is now infrared experimental, infrared camera measuring temperature. And you can see we see some of very similar behaviors where we're looking for broken symmetry. That is, is there patterns that are formed much like what is seen in developmental biology? And so here's a particular image. After polymerization, you can see there's a very regular pattern that has emerged from these materials. And while it may not be like, the pattern on the tiger or whatever, you still get the idea that somehow out of nothing came something which is and it's regular and it's recognizable. And so that's where we're heading to now. You can control conditions in a variety of different ways. If you can see it, there's a very long sort of pattern, and here's a very fine pattern. It's all by very small differences in the initial conditions that we executed that reaction at. And we're learning how to analyze this right now. And what's really exciting is on this plot is a property, how stiff the material is. And here we use a chemical dye that turns on at some temperature. And you can see there's a very strong correlation between the property and the colored zones, which are the hot spots in those unstable regions. And so together, this is sort of where our future is pointing, and thinking about manufacturing in these ways that can break symmetry and vary properties over space, depending upon if we can learn to control these reaction diffusion systems like frontal ring opening, metathesis, polymerization. And with that, I will stop at 50 minutes. I made the 50-minute mark. And there's the group of students. The faculty are in front. This was taken in 2017 before Scott White passed away. It's really in front of the Beckman Institute. Wonderful to bring this collection of people together in one laboratory and from several different departments working mechanical engineering, material science, aerospace engineering, and chemistry to work on problems, to come up with new ideas and really drive us forward. There's their names, and I mentioned several of them during the talk. And the funding for the work comes from largely from aerospace, the Air Force, and also the ONR, the Office of Naval Research, and then BP is the other major supporter, and the Beckman Foundation, who has funded some of the postdocs. I definitely happy to answer any questions. Really glad that I came and had a chance to talk to you, and would welcome questions at this time if there are any. Yes.
Is there any way to beat Thomson's water seal?
We have some very able people who are back in the lab, working on the next generation of coatings. I don't know if I don't know how far they'll get, and we don't really work on protecting wood, which is really what that's for, but that would be an interesting area to go into. It does work pretty good.
This is 35, 40 years ago. The SR-71 had a skin that could go and get very hot. Is that way out of date now?
No, actually, it's still it runs up against it's for speed reasons, right? That it hits very high temperatures, and so Mach 3, and so one of the reasons we got interested in vascularized systems isn't only for the repair, but it's for cooling. If we could provide a coolant to that skin, then we might be able to overcome some of the limitations in running these kinds of lightweight materials at very high temperatures. We have some success in that, but definitely is still a very much of a research endeavor at this point. No, there's one more question in the back.
Will the process work in a vacuum?
Like space?
Mm-hmm. Yes.
Yeah, there has not been tested, but not in an environment like space, but the composite manufacture that I showed, where there was a left and right image, one traveling to the left and right and one coming through, were done under vacuum. So in principle, yes, but I would say, like in space, we haven't done something exactly like that yet. In principle, it should be. It's a matter of where will the heat go, and how, will you be able to sustain that chemical reaction?
I know for aircraft structures, you have quite a bit of deformation. Airplane wings bend. Are you able to use, or have you explored the vascularization to promote results that you would like to see?
Yeah, that's a great question. So it turns out the epoxy materials that are used, for example, in the 787, the property that you're getting at, how much deformation can they withstand before they fracture, is a process that is toughness. Toughness, you've heard of the word toughness before. What it means scientifically is resistance to damage, resistance to crack growth. And so to prevent catastrophic failure when that wing bends up, you want the material to be very tough, to be very resistant to propagating a crack. Our materials are actually quite a bit tougher than epoxy materials. And so they're tough enough that the vascular channels should be able to withstand the deformation of that wing as the plane lifts off, and as the plane is flying and the wing is bent upward like you see it. We think we have a tougher material than conventional epoxies, a more resistant to damage material than conventional composites. By the way, this is a reaction you can do in your home. I'll warn you one thing: dicyclopentadiene stinks. And so there's a funny joke that goes with this. Is like, we originally had dicyclopentadiene encapsulated in those microspheres, and so dicyclopentadiene really it stinks like, I can't stand the smell of dicyclopentadiene, but you could imagine if somebody dropped a wrench on the airplane wing, and you would be like, I'm not flying in this plane, it stinks. And so that's sort of an automatic self-censor right there, as your nose is like a great sensor. Don't fly in this plane, it stinks, literally.
So this is more of a reaction scaling up kind of a question. Do you observe a difference in the FROMP reaction rate in the axial direction versus radial direction?
So in the tube configuration, the beginning is always a little difficult to nail down, like, what's going on there. But while I won't answer your question exactly because I don't know, that's the truth, I really don't know, like in that very beginning, is it going faster in the radial dimension than the up and down? What I can tell you is there are convective forces at play. For example, the velocity is different in the descending direction than in the ascending direction. And that's basically where's the heat going, right? Is heat going up or down easier? And so aspects like that do matter. And so in principle, it should be the same in whatever direction, axial direction or lateral direction that you're going. I'm curious if you thought of why it might be different.
Well, the pictures that you showed, in one of them, it appeared that the front was lagging behind as you approached the wall.
Oh, right. So that was because the walls were removing heat, and so it was a little cooler on the walls, and so what was taking place, that shape that you saw was a reflection of the heat being lost to the surrounding environment.
So this is a seaside town. There are a lot of people with boats, and they're made of composites. There's even a very well-known boat manufacturer here. Is there a polymerization system that you could think of that would be activated by water intrusion into the epoxy that would trigger the cell?
Oh, that's so it depends on what the substrate is. So, for example, one of the things that we have worked on pretty unsuccessfully at the moment, but is if you had an underlying iron-based substrate, so steel, for example, and you could do a corrosion prevention. We would like the substrate to actually be involved in the chemistry that triggers the repair. So we haven't thought about the water from, but water from, say, the sea to trigger the polymerization. But we've thought about the substrate, the other side, being able to be involved in the triggering process. And so corrosion prevention is something that, we would like corrosion to be able to trigger a reaction. So if there's a problem, as it appears by corrosion, we'd like to use the chemistry that's involved in corrosion to kick off the polymerization, but not the other way around, which is an interesting idea as well. If you want to be one of our first customers for MetaPrime, so we can say who's using it, we can point to people. Remember, it's a little more expensive up front, but a lot more labor intensive down the road. So I'm here selling MetaPrime. I should put that disclaimer out there.